Hello, everyone. Today we're going to be talking about temperature and heat, and we'll get to heat transfer in the next video. Um, but I wanted to talk about some general aspects of temperature and heat, and then get into phase change and temperature change and how that works. So, just a first few key points here. Um, we really can't talk about temperature without first talking about thermal equilibrium, where the simple definition is that objects are at the same temperature, meaning that they don't exchange any heat. Um, they're at the same temperature, thermal equilibrium. It's just what it sounds like. I guess you could think of when we think of equilibrium when we're doing our kinematics, right? We have like a balance beam in equilibrium. Nothing's moving. Everything's the same. Um, and equal. So I guess that's the way to think about it. So just wanted to introduce that concept and make sure that we're all on the same page when we talk about thermal equilibrium and what that means. Next concept is thermal expansion. But when substances are heated, they expand, and we have some equations here that help mathematically explain what's going on. So we have a linear and a volume equation for expansion of substances, that delta L and that delta V. These are given, the alpha and the beta are coefficients of expansion, either linearly or in volume terms, and those are material dependent. The L naught and the V naught are uh, how big the substance was before it was heated, and of course the delta T is the change in temperature that the substance goes through, or the material goes through. So when you're presented with problems that have to do with size change, make sure that you're using the right one. So if it's talking about a linear, usually referred to a bar or a cylinder that's heated and then expanded linearly. Volume, usually like a cube or a box or even a sphere. Um, so make sure you're using the right um, thermal expansion equation for whatever shape you're looking at, but also that alpha and beta, make sure you're using the right material specific um, coefficient of expansion. Um, so those, when you're presented a problem such as this thermal expansion, make sure that you list out the parameters that you know and the parameters that you want to find or need to find, and then you can play with the equation as you need. The last main part that I want to get to, and we'll do a couple of practice problems with this, um, is specifically with temperature and phase change. Each of these requires energy or gives off energy, and that is defined as the Q um, that you see here. And so for a material that's going through a temperature change, we can define the energy required for that or given off for that as C is the specific heat of that material, the mass of the material, and then delta T is the change, the temperature change that it goes through. For a phase change, we have that the energy is equal to the mass of whatever it is times the latent heat of fusion or vaporization, meaning it goes from a solid to a liquid for fusion, and vaporization is from liquid to a gas. So both of these give us a Q, depending on if it requires energy or removes energy, then we'll have a positive energy or positive Q versus a negative Q. So we need to be careful with that too. One last thing is that sometimes in problems uh, we're given the Q in order to find M or to find C or to find L. And sometimes that Q is hidden in a power term. So if you remember, the power is um, defined as change of energy over change in time, or P is equal to E over delta T. E here being energy, we can rearrange that equation, bring the E over and the P over. Well, no, I'm not bringing the P over. We're not bringing the E over either. We're bringing the T over. Excuse me, let me get rid of all of those because that's just silly to have on there. We're bringing the delta T over to this side. So, and then replacing E with Q, and we get that Q, or the energy change, is equal to P times the amount of time that power is being provided. So, just an important thing to note in terms of the relationship between power and energy and Q, and then how to use it with our temperature and phase change equations. So specifically, with this phase change, this is one that I found I thought was very important to talk about. So I'll just read it and then we'll go ahead. So latent heat of fusion for water is given as 33 times 10 to the 4 joules per kilogram, while the latent heat of vaporization is 22.6 times 10 to the 5th joules per kilogram. And then here's the main question. What mass of water must be frozen in order to release the amount of heat that 1 kilogram of steam releases when it condenses? So the thing that we are looking for is mass of water that must be frozen. So we're talking about the fusion of water. So it's talking about the latent heat of fusion in order to release the amount of heat. So here's the thing also that we need to be concerned about. The amount of heat, so this is referring to the Q, or AQ, that 1 kilogram of steam releases when it condenses. So this, again, is talking about the phase change of steam back to water. So we know that we're looking for mass, but we're looking for an equivalent amount of heat in both of these situations. So we're looking for the Q of the mass of water that is being frozen, and a Q that steam releases when it condenses. So we can write this. We're looking for the Q that's associated with that phase change of water is going to looking for the equivalency of the energy that is released when the steam condenses. So because both of these are phase changes, we can then write M of the water, latent heat of fusion, is equal to the mass of the steam times latent heat of vaporization, which is the phase change equation above. So if we're on that, then we can simply solve mass of water, or the ice, because the water is turning into ice. Sorry. We solve for that, we plug in the numbers, and we find that it's 0.8 kilograms of ice in order to release the same amount of heat that 1 kilogram of steam releases when it condenses. I hope that makes sense. So we'll go on to the next part. If you have questions, please leave comments and let me know. So again, focusing on this temperature and phase change. I want to, this is around the internet and you can find things about this. I just wanted to go through it again because it is really important. It can get kind of confusing when you're doing this, and so I want to keep it in general terms. You may not find a problem that's exactly like this, but hopefully you can take pieces of it and pull it out for whatever specific problem you're looking at. So a general phase change problem that is the whole gamut. You calculate the total amount of heat absorbed when a mass of ice at a temperature that is below freezing is converted to steam at a temperature above the boiling point. And for this, we can look at the heating curve for water, where on the y-axis we have temperature, on the x-axis we have the amount of heat added, or the amount of Q added to the system in order to complete this change. So here's the steps that we can go through and do. First, before we can start melting the ice, we have to heat the ice to 0 degrees because that is where it begins to melt. So that is this region of the chart. This is number 1. If it's just changing temperature, right? We're not changing phase yet. We're just changing temperature. We have to get to that 0 degrees. Then we need to use this temperature change equation up here. So here's our number 1. All right. So once we get that ice that is below freezing up to that freezing point at 0 degrees Celsius, then we can start to convert the ice into water. Then we can start the phase change. So then this part where it says melting is our number 2. So we can use this equation on number 2. And there we can then find the amount of energy required for that phase change. Oops, wrong way. Once all of the ice has been converted to water, once that phase change is complete, then the energy that we are putting into the system, the heat, can then heat up the water, the now liquid water, to 100 degrees, to that boiling point. We can't go all the way up to our final temperature, which is above the boiling point, because first we have to stop at the 100 degrees boiling point so we can do another phase change. But first we have to heat. So that's this third step. And we are heating. So we need our temperature change equation. Then once all of the mass of liquid that we have is now at the 100 degrees, now we can start converting to steam. Now we can start going through the phase change. And that is word number 4. So we can use our phase change equation at our vaporizing point here. And once all of that energy that we are putting in has been used to change phases, then we can finally heat the steam the rest of the degrees, or the temperature that we need to get to. So that is our final step here, our number 5, and we are using a temperature change equation to get the rest of that gas up to the required temperature. So again, you may not find a problem that goes through each of these steps and may be going backwards. But the point is that if you're going from one phase to another phase, you have to make sure first that you are at the right temperature or in between the right temperature, right? So if we started, instead of having an ice below 0, if we started right at 0, we wouldn't have to get it back to 0 before it starts doing a phase change. We could just start at number 2 and convert ice into water. That makes sense? Hopefully it does. So if we want to put this in equation form, oh, let me move me. We can say the total amount of heat that is used or absorbed in this system, Q total, is equal to Q from 1, Q from 2, Q from 3, Q from 4, Q from 5, and added all those together. So if we then go through and put in our temperature change or phase change equation, then we get something like this, which looks lovely. But if we kind of take things out and move things around, take out some of the zeros, then we end up with this. Essentially, it's the sum of all of these various steps. And like I said, the problems that you'll be faced, you probably won't get this whole big thing, but at least you can then go through and say, even if you write out this whole thing, then you can say, well, I don't need that component. Let's see. Like I said before, if we start at something that's at 0, then we don't need this because this just goes to 0. So we can just cross that out. Or maybe we go right up to 100 degrees. We don't go above 100 degrees on our steam. Then we can cross this out. So then we're just left with these 3 terms here in the middle. So hopefully that makes sense, but I think it's very important to make sure you know how to implement this with your phase changes versus temperature changes. And hopefully this general idea helps. If not, please leave comments. Please let me know, and I can help with that. So thanks.